Ờ, ờ. Cek cek. Ini Pak. Hello. Larry，才做 assignment 最后一题了吗？做了，你做出来了，好像少了一个 condition 哦，你做得出来啊？FMC 你算出来是什么？如果你可以算出来的那个东西，第一个 term 那个 f to the derivative value at c，如果没有跟你讲的话，好像不知道是什么，你 check 一下，好像少了一个 condition。MC，为什么是零？哦，因为它包了第一个 condition。哦，它包进去第一个 term，这样 OK 哦，这样它很恶心耶。前那个老师真的是。啊，给你们讲一个小秘密，就是我拿的这个 course 不是我以前有一个老师很恶心的 content 来的，就是怎么说呀？他教很快，他没有理我们的，他就是 proof 啊，然后呢，还要 expect 我们会算也会 proof，所以我们不会算，他不要学 proof，被逼着学。嗯，but 你们比较好啊，因为你们还有 analysis，我们没有，我们直接进 analysis，第一年第一个 sem 没有 calculation，呀，就很辛苦哦。我跟你们一样的，我也是天天在骂老师的，跟你们一样，所以我知道你们的讲，你们的心理想什么，所以就说，如果你们有什么问题，你们就尽量告诉我，如果我能的话，我就可以帮助你。好，呀，OK。All right. I think we should continue. So yesterday we spent about, I think, 20 minutes on calculating the integral, the Brooks integral on x, fx equal to x, linear function. Okay, from a to b, where we get b squared plus a squared equals, oh, sorry, the Brooks integral of x from a to b is what? B squared plus a squared over 2. Okay, this is what we computed yesterday using the boot integral. I will post out the lecture notes soon. I haven't rewrite the part for the yesterday calculation. So after I done that, I will post it. So actually, I wanted to spend time to talk about the integral of quadratic function, but I guess we spent too much time yesterday. So I would encourage you to try and compute the integral for x squared, say from 0 to 1, okay, yourself. Okay, I will include it into the lecture notes. Okay, does it make sense? Okay, no. So I'll try and define this partition and then try and compute the Brooks integral. The choice of partition is what? Um, is quite free, okay? But normally the partition we use is divide by 1 over n. Okay? Divide by 1 or 1 over n. You also can divide by 1 over 2n also can. Correct. Okay. Yeah. It's quite flexible. Okay. Okay, I suggest you to try this example, okay, I will include inside the lecture notes later. Okay, yourself. It's similar to how we compute the one for x. Okay, this one is x squared. Right. So integrate from 0 to 1, x squared is what? What's the integral? If you use calculus 1. What's the antiderivative of x squared? Okay, so you evaluate from 0 to 1, you get 1/3. Yeah. So if you use this rectangle business, which is the book integral, you will also get 1/3. Okay. So that they are the same. Okay, no? Okay, can you try yourself at home? I will include this into the lecture notes. If we have time, maybe we can visit more, and then I'll put some more exercise into tutorial. You can try more exercises. Okay, so next, so today we will give what is the sufficient condition, okay, for f to be integrable. What do you think? Huh? What f have to satisfy so that f is integrable? Continuous. Okay, we just need continuity. So we will prove that continuity will imply integrability. Okay, so if f from a closed interval, this is quite important here, closed interval here, from a, b to r, function is continuous, then f is integrable. Okay, then f is. Why this closed interval here very important? Do you know? What property does a continuous function have if you define from a closed interval? Hmm? Anyone recall? If you have continuous function on a closed interval, means what? Huh? It is uniformly implies that f is uniformly continuous. What does uniformly continuous mean? For every epsilon, there exists a delta such that for all xy, such that the distance between xy is less than delta, then fx minus fy is less than epsilon. So this delta can work for all xy, every x and y. Okay, so meaning if you have an epsilon, you just need one delta to control everything inside your domain. Okay, so that fx minus fy is within epsilon. Okay, so it's very strong because for every epsilon, you have a delta that works for all xy. Okay, for every xy, you just need one delta is enough for uniform continuity. Moreover, what else? F is continuous means what? What can you talk about the value of F? Huh? What can you talk about value of F? F is continuous. F string value theorem says what? Huh? What does F string value theorem says? If F is continuous, then what? F attains its maximum and minimum. Meaning what? This F is actually bounded. There's a top, there's a bottom, there's a maximum, there's a minimum. Okay, and it attains the maximum and minimum. And maximum and minimum. In other words, F is bounded. Okay. Okay, so so there are few steps to reach our goal here. Okay, there are few steps to reach our goal. How to prove F is integrable? Yesterday we gave a criteria to say that F is integrable. What's the criteria? What's our goal here? For every epsilon, there exists a partition P epsilon of AB such that we can make the upper sum and lower sum as epsilon close to each other. Okay, this is what we had yesterday. Okay. If we can prove this, then our function is integrable. If our function is integrable, then this has to be true. Okay, so we have uniform continuity, we have f is bounded, then we try to find this p epsilon here. Okay, we try to find this p epsilon here. So how are we going to use the uniform continuity and boundedness here? Remember, when you take the difference between upper sum and lower sum, what's in upper sum and lower sum? What's inside upper sum and lower sum? You have length and width, right? Length is what? The value of f. Yeah, the value of f, right? The length. The width, the length of your sub-interval. Okay, the length of your sub-interval. So you see, we have uniform continuity, we have boundedness. So boundedness here bound what? You can bound the value of f. You know how far value the f can go, okay? Or how small the f can go. So there's a range for all the f, supremum of fx and infimum of fx. How about the width? How to control the width or the length of the subinterval? You should use the uniform continuity. There's a delta for you to use there. One delta can work for all xy in the domain. Okay, so we try to piece these things together. Okay, let's see how we piece these things together. Okay, so the first step. Okay, so the first step we will do is we want to try and control the image of f. Okay, we try to control the image of f. So the first step, we'll try to control image of f first. And we want to control the range of it. So how do we control it? So just now we say that since f is uniformly continuous, okay, then even an epsilon greater than 0, there exists a delta, call it delta epsilon over b minus a, okay, such that what? If I can make sure that all the domain point within delta close to each other, which is this specific delta epsilon over b minus a, it will implies that fx minus fy is less than epsilon over b minus a. Okay, so you might think that this over b minus a is a bit fancy here. It's a bit fancy. It is quite fancy because later we will use it to cancel out something else so that in the last step we will get epsilon only. If you want to just keep at epsilon, it's fine. Okay, but in the end you won't end with epsilon. That's the only thing. Okay, so let's see later. We will justify why we make this epsilon over b minus a choice. Okay. Okay. Next. So for this epsilon, we want to find the partition that works. Okay. So now we are trying to fix. So now we're trying to find our partition p epsilon. Okay, let's find what p epsilon will work. So for this bound to be true, you need to make sure that your x and y is delta close to each other. So how should we choose our partition? We want to make sure our subinterval is smaller than this delta, so that we can have this f bound. Okay, so that we can bound this f using this epsilon. So we need to pick our, so okay, Maybe let me draw to you what we are doing here. Otherwise, you think I'm a storyteller. Okay, so let's say you see x and y. So the difference of x and y should be less than delta over epsilon b minus a. Where is b minus b and a? So b and a should be one of them should be on the right hand side, the other should be on the left hand side like this. So as long as you can make sure, okay, x and y is within delta each other, you can make sure that your fx and fy, the difference here is also less than epsilon b minus a. Okay. So how do you choose your partition then? You need to choose your partition, of course, how to say, smaller than this distance here, so that everything within this delta epsilon over b minus a, you will get this bound here. Okay. So how do we do this? So we choose a number n so that what? So that um so that n is greater than greater than, let me see, greater than, let me check. So we want to make sure that b minus a over n is less than delta. Okay, so this is how we want to pick it. Okay, we want to make the, you see, what is b minus a? B minus a is the length of the whole interval, right? Okay, so we want to check how small we want to divide it. How small we want. Okay, we want to divide it so that the sub-interval has the length less than delta, so that we can have this property here. We can apply the uniform continuity property. Does it make sense? Make sense or not? Does everyone get what is b minus a over n? 把 b 减 a 除成 n 份 ，OK？n 份要多小呢？要小过这个 delta。为什么？当 x 减 y 小于 delta 的时候，我们才能够保证 fx 减 fy 是被 epsilon over b minus a 控制住，可以吗？明白吗？明白吗？OK，我要这个 partition 够小，so that 我可以 apply uniform continuity，合理吗？OK，多小呢？我要让 b minus a over n 是小于这个 delta，meaning what？meaning n 要大于 b minus a over 这个 delta，OK 吗？OK，所以怎么找这个 n？你就要保证你的 n 是大于 b minus a over delta。为什么可以找到？因为 Archimedean make sense？ OK 啊 ？OK， so in this case, right? What is our b p epsilon here? So our p epsilon will be x0, x1, sn， 对吗？你把东西切成 n 份了，对不对？你肯定有 n 加一个 point。OK， 好像我们以前小时候小学啊，算有几个电灯杆，电灯在3 米里面有几个电灯杆，如果0.5 米有一个电灯杆啊，每次忘记算第一个的，因为第一个一定有谁嘛，零一定要有一个电灯杆，然后0.5就有一个0.5就有一个0.5，明白吗？所以现在我把 b minus a 切成 n 份，所以里面应该有 n 加一个point。S0 to Sn. So S0 should be A and then Sn should be B. Okay. Okay. But so what are these xi? How do we define this xi? This xi is simply a plus I times b minus a over n. So you are how far you are from the first endpoint. Okay. So I is going from where to where? I should go from 0 to n. Okay. So there you go. Every xn. Hello, testing. Okay. Hello. Okay. So what's next? Okay, so now we are ready to compute. Hello, hello, hello. 是麦没有电还是它的问题啊？Hello, hello, 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 hello. Okay. So we want to bound mi. We want to bound the value of f now. Okay. So how do we bound it? So how do we bound then? Um, let's see. So to compute upper bound and lower bound for this P, right? You need to know the supremum and infimum in every subinterval. Okay? In every subinterval. How do we call this supremum and infimum? So let's do some notation here. So denote mi to be the supremum of fx for x in xi minus 1 to xi. And we fix little mi to be the infimum of x in xi minus 1 to xi. Okay, so our job now is I want to show you that once we pick this partition, we can bound this mi and capital Mi and little mi, the difference of them in particular. Okay, we can do this bound. So our claim is, let's see what's our claim. So we claim that for every I, mi minus mi is less than epsilon over b minus a. Okay or not? Is this clear or not? Why we claim this? Remember how we pick our partition. How do we pick our partition? How do we pick our partition? Okay, so remember how do we pick our partition? Sorry. Yeah. B minus A over N. So we pick the partition such that B minus A over N is less than delta. So the length of the subinterval is less than delta. Okay. So we want to prove this. This since what? Since F is continuous, okay, there exists X max and X min in the interval xi minus 1 to xi such that f max fx max equals to mi and fx min is equals to little mi. Okay, agree? Okay or no? Extreme value theorem. Maximum and minimum are attainable. Okay. All right. So how do we show that? So what's our goal here? So we want to show that f, so mi minus little mi is less than epsilon over b minus a. Okay. But remember that we can get this inequality from the uniform continuity property. Okay. So how do we use uniform continuity property here? So let's check what is x max minus x min. Okay. X max as x min here, the distance here should be less than or equals to xi minus 1. Why? Because x max and x min live in the subinterval of xi minus 1 and xi. But this interval, how we choose it? We choose that such that this length here should be less than delta, epsilon over b minus a. Okay, we choose it to be less than delta. So once we have this, by uniform continuity, mi minus mi here is what? So we have that mi minus mi, which is just fx max minus fx mean here should be within epsilon over b minus a. Okay, this is uniform continuity. As long as I make sure that my point in the domain is less than delta, okay, then I can make sure that the difference of f is less than. Yeah. Question? Got question? Question? Any question? Tanya, got question? No? Okay. So finally we need to check the inequality now. Okay, finally we check the inequality. Let's check. So we'll check the inequality. Inequality on UFP minus LFP. Okay. So what's the formula of UFP and LFP? So UFP should be the sum of I equals to 1 to n of mi xi minus 1 minus the sum of I equals to 1 to n of little mi xi minus 1. Okay. And what can you do is you can try and factorize them first to get mi, capital Mi minus little mi times xi minus 1. Okay. But for every mi minus little mi, what do you get? This thing should be smaller than epsilon over b minus a. Okay. So what's the good way? Why we want to bound mi minus mi here? This epsilon over b minus a doesn't depend on I. It doesn't depend on I. Okay, so we can put it out. It's just a constant. But again, what is this sum here? Sum of this sub-interval here is what? It's just b minus a. Okay, so that's why just now we want to bound our mi minus mi, so capital Mi minus little mi to be epsilon over b minus a, because we want to cancel out with this b minus a. So we get epsilon. Okay, does it make sense? Okay, no. Testing. Okay, does it make sense? Okay. Okay. Can or not? Make sense? Okay. Okay, good. Let's continue. Although we say that continuous function must be integrable, does it mean that integrable function must be continuous or not? Is the converse true or not? Is the converse true? Actually, it's not true. Okay, we can have integrable function that is discontinuous. Okay, discontinuous. I'm not sure you remember that last time we talked about when we integrate the surface, okay, there might be a line that you cannot integrate, that's fine. You still have the integral. Okay, this is what we're gonna discuss now. Okay, so let's say we have a function, okay, it is 0 all the way. Okay, except one point. Okay, except one point. This point is a naughty point, x equals 0, equals to 1. Okay, that it want to be different from the other. Okay, very naughty one. So how does this function looks like? So everywhere else, it is just 0. Okay, everywhere else it is 0. Everywhere else it is 0. Only at this point here is 1. X and x. So we claim that this function is integrable. Do you want to guess what's the integral of this function? 0, yes. This integral should be 0. Okay, we will compute it using the rectangle way. Okay, we will compute it using the rectangle way. You see, for this function, right, you cannot use calculus 1 already, right? Can you use calculus 1 knowledge to do this? How to integrate this guy? This is not like a normal x function, x square function, polynomial function, or trigonometric function, right? So this is like a piecewise function. Okay, how do you do it? How do you do that? Using your knowledge of calculus 1. You can't quite do it, but we can do it using rectangle. Okay, we can use the partition in particular, upper sum, lower sum to compute it. So that's why we want to go back to definition of integral, because we can do more example. Okay, we can do more integration on more example. Again, not just functions. Again, not just functions. All right. So how do we prove this? So let's do this proof. So to prove f is integrable, what do you need to show? Hang Wei. What do you need to show f is integrable? Hang Wei. Ethan. No, we can't move on. We need to settle this. You need to show that the upper integral is equal to the lower integral. Okay, you must remember this. So we want to show that upper integral of f is equals to the lower integral of f. How do we define upper integral and lower integral? Huh? What is upper integral here? What is lower integral here? How about another Hanwei? What is the upper integral? What's the definition? Sub or inf? So the upper should be the inf, because if you do refinement, it keep decreasing. Okay, so you should be taking infimum of what? Infimum of all the upper sum. Okay, all the upper sum. Please, I must remember this definition. Otherwise, you can't do literally any study properly. Definition is very important. You have to get definition first before you start proving, start doing exercise. Otherwise, no need to talk. Okay, without definition, no need to talk. No talk. No definition, no talk. Okay, must have definition. So what is LF? Vincent? Yes, it's a supremum of what? LFP, supremum of lower sum. Because remember that when we do refinement, the lower sum will increase. Okay, the problem is this increasing will stop one. It will stop. It will stop. Why will it stop? Because the set is bounded above. Okay, bounded above by the upper sum. Bounded above means 什么？什么意思叫做 bounded above？有一个顶明白吗？有一个顶，所以你这个增长率是会停的。Okay? 有一个顶 bounded above。看到 ？Okay. So we need to prove this for every point. Sorry, yeah. Okay, good. So let's do this. We need to show for every p. It's quite troublesome. Every p here. Okay, so what do we do? Let's see. Okay, look at this question again. This question saying what? Then f is integrable on any closed bounded interval AB. Hey, what can this bounded closed interval AB be 的 ？AB 可以发生在哪里？有三种情况 ，there are three possible condition。AB 有三种情况，哪三种情况 ？Both AB is negative, or both AB is positive, or one of them is negative, but one of the negative must be A, right? So that B is positive. Okay. There are three possibilities. If A and B are negative, that means on the left of the origin. Meaning what? This function is zero. Okay, zero function is integrable. Last time we proved already. Or you can easily see that the upper sum and the lower sum on the left is always zero because the infimum of fx is zero, the supremum of fx is also zero. Similarly, on the right hand side here. Okay, so we can conclude that. What can we conclude that? If zero is not in AB, then f is just constant function zero. Okay, constant function zero. So it is integrable. Why is it integrable? Because what? UF equals to LF equals to 0. Okay? Because supremum of fx, infimum of fx are all 0, no matter what partition you take. Okay, because the function is just 0. The function only gives you 0. Okay. So now the only case we want to consider is if 0 is in, if 0 is in this interval here. Okay. So now suppose this case here. In the first case should be 0, not in. Okay. So how we prove this? So we will use the theorem again. Okay, we use the integral analytically theorem. Okay, to prove it. To prove its integrability. Okay, so what does the theorem says? When is f integrable? For every epsilon, you want to find a partition such that UFP minus LFP is less than epsilon. Okay. So let epsilon greater than 0. What kind of partition you want to construct here? Any idea? So let's get our picture right first. So let's get our picture right here. Always like my A may be here, my B may be here, content 0. So what sort of partition we want to build here? So that UFP is less than, so that UFP minus LFP is less than epsilon. Okay. What sort of partition we can put here? We can consider an easy partition here. Okay, maybe we set here minus epsilon over 3, here epsilon over 3. Okay, later you'll see why I want to make it over 3. So what's this partition here? What's the upper sum here? So upper sum and lower sum for A to minus epsilon over 3 and epsilon over 3 to B should be the same, right? It's just 0. Okay, but the upper sum and lower sum here is different. What's the difference? What's the upper sum in the middle subinterval here? It's 1 times 2 epsilon over 3. Okay, so this upper sum here is here. Here is the upper sum. What's the lower sum? 0. Okay. Always there's a point is fx equals 0. Okay, so in this case here, we can quickly compute that UFP. Okay, so we have to fix our UFP first, right? I mean P epsilon. So how do we pick our P epsilon? So I claim that this will work. Okay, why is this working? So you can see that this difference here is depend on epsilon, right? So what is this difference here? It's just upper sum minus lower sum. Upper sum is 2 epsilon over 3, lower sum is 0. So 2 epsilon over 3. So 2 epsilon over 3 surely less than epsilon. Okay, so we are done. Okay or not? So the main takeaway here is we make this difference depend on epsilon, and then it is smaller than epsilon. Okay, does it make sense? So you can pick maybe epsilon over 4 also can, epsilon over 100 also can. As long as the difference is less than epsilon, we are done. Because this is what the theorem says, right? You have to make sure your difference less than epsilon. Okay? Then you are integrable. Can or not? Okay, got question? Got question? Any question? Any question? Okay. If no question, right? So we are not quite done yet. We are not quite done yet. So, so what? So we are not quite done yet. We want to show that the integral is 0. Okay, so we only show that f is integrable. Okay, so why? So why the integral is 0 in this case? Huh? So if it's integrable, it means what? This integral should be equals to LF and equals to UF. But we know what is LF, right? What is LF? 0. Okay, so not that. Integral of f equal to LF. But what is LF? Is the supremum of all LFP. But LFP is always 0, no matter what partition you take. Okay, it's always 0. So supremum of 0 is just 0. Okay. Okay. Does it make sense? Okay. All right. So just now we forget a few cases. We only talk about 0 in the middle of AB, and then if AB avoid 0. What if the boundary point is 0? Maybe A is 0, B is 0. Is it still true or not? This condition here. What do you think? Okay, I give you maybe 2 minutes. Think. What if A or B is 0 now? Is it still integrable? If it is integrable, what's the integral? Try and think. I give you 2 minutes. What if A and B is or B is 0? Why cannot? You want B, you mean B is 0. Assume B is 0. Okay, assume A is 0. Sure. Sure. Mm-hmm. Wait. So you mean you set this as your A, right? Okay, and then set B here. Okay. So, and then, okay, how do you argue? Okay, let's say we want to refine here. You sure? You sure? I already give you a partition here. What is the UFP minus LFP here? For this partition here, what is the UFP minus LFP? Not quite right. Sorry? So, wait, let me write down. So this part is 0. So what is UFP here? 0 times, not 0 times, 1 times epsilon over 2 minus 0 plus 0 times epsilon minus epsilon over 2 plus 0 times b minus epsilon. Correct or not? So what is this? This is actually epsilon over 2. Correct or not? How about LFP? LFP is simply just 0 times epsilon over 2 minus 0 plus 0 times epsilon minus epsilon over 2 plus 0 times b minus epsilon, which is just 0. So the difference of them is epsilon over 2, which is less than epsilon. Okay. Yeah. Okay. So in both cases, what can you see here? You see the partition you set here, when epsilon goes smaller, you can see that this partition, like, how to say, converge to the line, converge to this discontinuity line here. But it converges to the stage that you can always bound it by epsilon. So the how to say, the contribution of this discontinuity here to the integral is like nothing. Okay. Because area of the rectangle, if I give you a line, what's the area of this line? No area, right? So you need to bound a positive width. Otherwise, this line, what's the area of this line? No area. Area is 0. So there's no contribution of this discontinuity point here. So you might ask, let's say I introduce another continuity, does it work? Is it still integrable? Yes, it is. If I introduce 3 discontinuity points, is it integrable? Yes, it is. 4, 5, 6, how many discontinuity points I need to introduce so that it is not integrable? Okay, this is another story. Okay, if it is countable, then it is integrable. Okay. Yeah. Okay or not? Okay. What time is it? 9:50. Let me see. Let me see how far we want to go. Okay, let's take a break. Okay, let's take a break, and then we'll come back to discuss the book sum, the relationship between the book sum and Riemann sum, and then we talk about a property on integrable function. Let's break until 10 o'clock. 哪一个？高超系那个，有这种联系过你，大有的，任意都有方法，为什么来说？差不多，但是你要 refresh 拒绝的，对。这个方面说都没有领证。这个对，这个不要做反了，是的，每次就然后这会有病，对，然后我死，这个三个分的这个就是你知道，像是这个就不要阅历，你可以把它变成你的那个，你要做的这个，就说你的 theory 在这个。and then 你再说这个东西的话，然后你可以用在一定的，这肯定这个东西你一定是具有，其实有一个用处的决定吧，干嘛？然后有用处嘛，因为你还是对 n 的是n 对啊，难怪我看你说 n 啊，这个告诉你啊，有多少个 number 你说高的 number 百个。就是说你不可能有超越这个号码的那个，没办法算。你可以懂它，可以保证。对，而且这个只是一个方法来，这个一个方面，这个方的方面，因为这是零零两零零，它是 prefer 的最小哦，它不止帮着 above 哦，它还对，而且你还知道它什么了，它不保证哦，所以这个东西这么重要，所以这样才用。对啊，懂的。啊，对对对，对啊，洗着，比如说 oil 找出来了。如果是普通的 Apple bar，没有人采用，没有什么这样，没有什么重要。我来看看这个是，对，第一是 oil 方面，哎不，第一是 exponential 方面。OK，啊是这个，因为它用 m u l t 对啊，对啊，这样 I guess 就是往这个，对啊，你可以用这个，你可以直接 apply 吗？比如说你可以 apply for integrability maybe n 啊，可以说有些 n 不符合，有些可以采用。那必须找你看电脑，我看一下。东西特别多。我觉得有些 n 也不知道你要什么 by n，对，因为这个小过 n 会有些就是我是写以前的，只是你买了之前，我们现在又不可以，对对对，还有 different 一个叫什么？哦，你看啊，它真的是不是所有的 n 都符合，还要大于 n 是吧？
对 n 就是到这个 epsilon，
应该是这样。
但是应该会比较简单一点，它只要 n 够数的双体。
哦，他是用到这一句吗？对，是利用 part n，所以是说，你要 vector，
这是做那个，我也是做。
对，你的 n f 就从 a 来，只有这个 n 哦，它会看我这个条件，之前呢都不一样。哦，之前可能会大于，说是先有这个 n，对，才有 a，还有 b two，来，还有 b two，这个题的，这个就是这个。就是那在一起在两上去可以。它 result 不是这样 frame，它的 result 想要说，有 infinite depending n 可以符合这个条件，然后是不符合，然后怎么去找那个 infinite depending n 呢？其实你可以用这个 n，就是给了一个，哦，我知道了，它这个东西是 depend on 这个 c 的，因为 c 被 fix 住，然后 epsilon 也被 fix 住，你要 fix 这两个东西。然后你就问什么 phi 什么 function 和哪一个 n 会符合，然后他就讲有限个 n 会符合，所以这个东西是他选择性，是他选择的这个包，然后他要问一个问题，就是如果我 fit 了这个包，有多少个体验会符合这个，他会，两个会为了回答这个问题，他解了点，哦，OK，这样子的，他的 idea 是他要结合。我 fix 一个 epsilon，我 fix 一个 c，然后这个 n 出来这个号，然后我要问一个问题，这个 torsion function 的话 n 有多少 n 会符合它想的公式在 n 啊，他给了一个 criteria，就是如果我能够保证 n 大于这个 n， 就所有的 n 以后都会符合。当然，这个大 n 从哪里来呢？我要保证他做这件事情，但做了这件事情，我就可以赢这事。所以这个是他的想法。所以你看啊，这个 proof 啊，不是随便他 proof B 再 proof A，是因为他真的是要走到第一线，他才会把 A 想出来，就有点像雷吗？其实 A 其实是个雷。assume 这个雷吗？先我们就可以拿到这个真的这个证明到来的做这个啊，你可以这样讲。当然，你也可以 proof 雷吗？现在 proof 这个。没有影响，没有影响，它就是直接用语道的。可是你要确保你的语道。And then 你，我觉得你可以做一个 example 出来咯。比如说你 fix 那个 oil 分，你 fix 一个 epsilon，然后你 prove 一下，那个 torsion function 要 apply 哪个 n 会符合这个条件。可能你给一个 example 咯，符合那个不符合就可以了。那个做的你的那个三个 part 开始 show 一个东西。
啊，什么上课？
要上课几点了？
差不多。
OK，我等一下再问。Hello, testing. Okay, so we will go through what is relation between Riemann sum. Are you guys reminiscing of this not page? 有印象吗？哦，啊，有印象吗？什么印象啊？这从哪里来的？
calculus one 来了，对，我就是从你们 calculus one 拿来的，我去跟那个 calculus one 的学生讨的，有印象吗？啊，不是你们老师写的，这只是学生写的吧？但是有做过这题吗？应该要有做过啊，就是你们 calculus one 里面的呢。啊，还记得怎样做吗？看一下他怎样做啊，看一下他老师教他什么。第一步，你也是找 partition 嘛，来，他选的 partition 是什么？b minus a over n 咯 ，OK，regular 的普通的。And then 他选的 what he choose for the fx star? How he choose the fx star? Is he choosing supremum or infimum or anything? How he choose 呢？随便 choose, but he choose in the way that this xi is minus 1 plus 4i minus n. What's this? You see, the partition delta x he choose is 4 over n. So what does it mean? It split the minus 1 to 3 with subinterval length 4 over n. And then the fxi star is what? Is minus 1 plus 4i 1 over n. So meaning what? It picks the left endpoint. Pick the left endpoint. But this one is x squared. S squared means what? The function is increasing. So the left endpoint is the lower sum. So actually this Riemann sum is doing lower sum computation. So this Riemann sum is a lower sum computation. Does it make sense? Yes, question? Minus 1 to 3, yeah. Oh, increase on 1 to 3, but decrease from minus 1 to 3, right? So it's like, so in this case, it becomes a mix of from minus 1 to 0 is the upper sum, and then from minus 1 to 3 is a lower sum. Correct or not? Okay, draw this picture. Draw the picture up. No, yes, not necessary because this is a Riemann sum. So the difference between Riemann sum and the book sum is, let's go to the definition here. You see, the Riemann sum here, what you consider for your fxi star here, you just take xi star to be arbitrary point in the interval xi minus 1 to xi, arbitrary point. See, I highlight this, arbitrary point. Okay, any point. So they pick a easier choice, they just pick the left endpoint of your subinterval. But you see, how do you see? Let me move this picture to the side. Let us draw this picture. Let's see what this guy is doing. So let's draw our picture. A very good point pointed out by Jack. So if we consider minus 1 to 3, what happened? In the interval of minus 3 to 0, it is decreasing. Okay, but in the interval from 0 to 3 is increasing. But our convention of our interval is what? Okay, so you see, what do we pick here? So here we pick minus 1 plus 4 over n. Okay, and then so on, and then so forth. Right. So on the left-hand side here, if we just pick left endpoint, the f on the left-hand point, what we pick is really the upper sum. Okay, but if we pick left endpoint in the interval from 0 to 3, what we get is the lower sum. Can you guys see it? Can see or not? And then these add up together is our Riemann sum. Okay, so this Riemann sum is a mix of upper sum and lower sum together. Does it make sense? Yeah. But in the end, remember how you show that this Riemann sum converge. You just simply take n to infinity. Okay, you simply take this n go to infinity. So the mixture of upper sum and lower sum are also conversion. So this is Riemann sum. But for our case, we need to make sure our upper integral equals to lower integral. Does that make sense? Okay, so let's see how these two are connected. Okay, let's see how these two ideas are connected. So we need to make some definition first so that we can speak properly, speak on page. Okay, so let's see a relationship between the book sum and Riemann sum. Okay, so how do we define Riemann sum? So we need to start from definition. Okay, like what I said, no definition, no talk. Okay, don't talk if you don't have definition. So let f be a bounded function again, okay, on AB. And obviously what? We want a partition. Okay, we want a partition. Let P be a partition of AB. Same, it's the same, it's the same construction. But now we have a new thing here, okay? We have this C, okay, which is set of Ci to Cn, such that this is the Xi star you see in your calculus 1 notes. Okay, so this is some point inside the subinterval Ti minus 1 to Ti. Okay. Then how do we define this Riemann sum here? Riemann sum. How do we define this Riemann sum here? So this Riemann sum really depend on, it correspond to a partition and a set of points Ci. Okay. So it depends on these two things. So the Riemann sum is, we call that S of FPC. So last time, our upper sum and lower sum only need partition. Okay, only need partition. But now this Riemann sum need a special C here. What is this C doing here? This C will tell you what value of F you are using. You simply apply F to Ci. Okay, for each subinterval here. So FCI here become the length of the rectangle. Okay, we still have Ti minus 1 as your width. But the length here is not the supremum or infimum. It's just a random height inside your function. Not too random. This height have to exist in between Ti and Ti minus 1. Okay, Ti minus 1 to T. Does it make sense? So from this definition, what can you infer? What can you infer from this definition here? How do you compare this Riemann sum to lower sum and upper sum? What do you think? How to compare lower sum, upper sum, and Riemann sum? Given the same function, same partition. How do you compare lower sum, upper sum, and Riemann sum? What do you think? Good. Riemann sum is in between upper sum and lower sum. Why? Because how do you pick for lower sum? You pick F to be the infimum. How do you pick F for your upper sum? You pick it to be the supremum. But Riemann sum, just any number in between supremum and infimum. Make sense? Okay. So Riemann sum is in between upper sum and lower sum. So I can show you this picture here. So you can see, given this function here, okay, if I have a partition, okay, T0 to T6, so T0, T1, T2, T3, T4, T5, T6, and you can see if I form upper sum is the orange, is the yellow part, okay, it's the upper sum. If I form the lower sum is the red part. Riemann sum, how do we pick Riemann sum here? This is quite regular. We pick the midpoint. You see, Ci is in the middle of T0 and T1, and then C2, C3, C4. And then you also form the Riemann sum here. Whilst the height of C1 is this point here, then I form the Riemann sum here. Whilst the height of C2 is in the middle here. Okay, then we form the Riemann sum here. Does it make sense? So you can see that Riemann sum, the orange one, is always in the middle of the yellow one and the red one. Okay, so Riemann sum is bounded below by upper sum, and bounded below by lower sum, and bounded above by upper sum. Okay, that's right. Everyone get what I said? Okay. Okay, good. Okay, good. Right. So, how do we get this Riemann? So, okay, let's see. How do I motivate this? Okay, next, we want to see that, let's say our function is the root integrable, okay? Let's say upper sum is already equal to lower sum. Can we show that Riemann sum also converge or not? Okay. If upper sum, you see, just now we show that every Riemann sum is bounded above and bounded below by upper sum and lower sum. Let's say upper sum and lower sum converge. Can the Riemann sum also converge or not? It should be, right? It's like a squeeze theorem, something like that. Okay, so we can show that. But how do we show that? So how do we show that? So let's define a term first. So let's define T equals to T0 dot 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 to Tn, the partition of AB, and let delta greater than 0. We will say that P is finer than delta if Ti minus 1 less than delta for I equals to 1. Okay, so you see, here we introduce a condition on partition. Okay, if you have the length of every subinterval less than delta, we'll say that this partition is finer than delta. Does it make sense? You see here, every subinterval here should be less than delta. Sorry, here is Ti. Okay, Ti minus 1. Okay, if every subinterval less than delta, then we'll say that this partition is finer than delta. Okay, so what we're gonna to prove, not now, actually is in the assignment. I'll put it in. I'll give you hint to prove this as well. So let's say f is the root integrable. Okay, on AB. Then we will show that for every epsilon greater than 0, there exists a delta greater than 0 such that for every P partition of AB, which is finer than delta, okay, which is finer than delta, and for every possible choices you can pick, okay, then we have the Riemann sum equals to the Brooks integral you computed. Okay. Can everyone understand this statement here? Let's say our function is the Brooks integral, upper integral, lower integral equal. Then we can show that for every epsilon, there is a delta. Okay, such that for every partition which is finer than this delta, okay, any partition that your subinterval is less than delta, the length of your subinterval less than delta, then
For every C you pick, okay, from the subinterval, the Riemann sum minus the boot integral should be less than epsilon. Okay, you can prove this. Okay, we will do it in the assignment. So how to prove this? There are two cases you need to consider here actually. You need to consider f is continuous and f is discontinuous. Because integrable, like what we have done just now, right? It doesn't guarantee whether you're continuous or not. And so you need to split into two cases to prove this. And from here, we will say that, so definition, if a function satisfies the result of the theorem above, then we say that f is Riemann integrable. So what's the result of this statement? The result here is for every epsilon, okay, you can find a delta such that for all the partition, you make sure that the length of subinterval less than delta, and you pick any, okay, any choice of C from every subinterval. If your Riemann sum minus some number, okay, can be always less than epsilon, then we will say that this function is Riemann integrable. So Riemann integrable just says that Riemann sum has to convert to some number, but the Brooks integrable, you need to make sure that upper integral equals to the lower integral. Okay, so this is the difference. Does it make sense? Okay, yeah. Okay, so from this theorem, what can you infer? You can infer that actually the Brooks integrable implies Riemann integrable. Okay, so if you have the Brooks integrable function, it must be Riemann integrable. So meaning whatever you did in analysis it works in calculus 1. Okay, what we did, the Brooks integrable is imply everything inside your Riemann integrable. Okay, but is the other direction true or not? If you have Riemann integrable function, is it the Brooks integrable or not? Any idea? If why? 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 If a function is Riemann integrable, satisfy this property here. Is it the full integrable? So if you take the upper integral, is it equal to the lower integral or not? Give you 2 minutes. If you have a Riemann integrable function, is it the Brooks integrable or not? Yes or no?
Yes.
Why? And then?
So I just the function sum.
Everything, not quite right. Yes. But you see, upper sum is one of the Riemann sum. Lower sum is also one of the Riemann sum. So Riemann sum converge, meaning this upper sum and lower sum should also converge. Correct or not? It's like a subset. Correct or not? The book sum is more restrictive because we pick the infimum and the supreme. But Riemann sum can be any point. So meaning what? The book sum is an Riemann sum.
if Riemann sum converges, this subset of numbers should also converge. Right? Okay or not? Okay. We will make this question into your tutorial. Actually, it's in the textbook. Okay, I'll make it into tutorial. Okay. So we will show that Riemann sum implies the book sum in the tutorial, and then I put in the assignment the book sum implies Riemann sum. So corollary is they are equivalent. Okay. No matter you want to do Riemann sum, you want to do the book sum, okay, you will get the same integral. Okay, so the result is not only the book integrable equivalence to Riemann integrable, actually the integral that define is the same. Okay, give you the same number. Define differently, but give you the same result. Does it make sense? Okay. Actually, there are more integral than the book Riemann. If you look at the J's book, there's a lot. Okay, a lot more than this. Okay or not? All right. Any question about this subtopic here? We'll do it more detail in the tutorial and also assignment. Okay, tutorial and assignment. Hey, by the way, I put out the assignment the tutorial for last week. Did anyone look through already? Not yet. Okay, please look through. And have you read last Thursday or Tuesday lecture notes? Everyone read already? Did you read how I define the logarithm trigonometric function? Please have a read, because that's how we define the logarithm and exponential function and irrational power of x of positive number and trigonometric function and inverse trigonometric function. Okay, how we define sine, cos, tangent, arcsine, arctangent, arccos. Okay, why they are like why the derivative of arctangent, arcsine is 1 over x squared plus 1, something like that. Why turns into derivative? That's the chapter of that. Okay, definition. Okay, it's a result on how we define sine function. It's a result of how we define cos function. Okay, please read through. So it is like this. Maybe if you read the textbook, it's very hard to follow. But what I did is I reorganize the idea. Okay, I reorganize the idea so that you know how to get the main point from the textbook. Okay, because in the textbook they write in like a story. So when I ask question, then you will know, oh, this part is what I need to focus when I read this paragraph. Okay, so try and read the textbook. Use my question to read it. Okay, so every answer in the last tutorial, you can find it in the book of Fitzpatrick. Okay, every part of the question, you can find the solution in the Fitzpatrick. If you can find the right solution, that means you understand the textbook already. If not, read again. Please read. Okay, please read, and then please answer and do the tutorial. Okay. Does it make sense or not? Does it make sense? Yeah. Okay. 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 Wait. Maybe I think now it's 10:27. Okay, let's see. We will introduce a few properties of integrable function now, and we will see if we want to prove any of them, because surely we cannot prove all of them because we don't have so many time. But to prove all of them is just a routine. Okay, it's just a routine. 知道什么叫 routine 吗？常规，就是什么叫常规？华语不好啊。好像你天天扫地那种叫做 routine 哦，就是你就平时都要做的事情。Like what habit? Something, not quite, but even if it's not habit, you still need to do it. Okay, yeah， 就是一些比较日常的 ，OK， 日常的东西。 All right, so let's go through some property, and then we will decide which one we want to spend time proving it. So any property of integrable function you can remember or not, out of your mind? Any of them you can remember from what you have learned? Anything you can remember or not, out of your mind, about integrable function? What do you mean continuous? Linearity, right? Linearity says what? So okay, let me make some proposition first. Linearity says what? Linearity got how many things, first of all? When we talk about linearity, this word linearity is very specific actually. So there are two things inside this linearity. What is the linear algebra learning? Linearity or linear algebra. So what does this linearity do? Sorry? Plus? 对，是怎样 plus？ F plus G 做什么 ？F plus G 做了什么事情 ？Sorry？ Oh yeah, good, very good. So good, very good. So linearity. If F and G are integrable, F plus G is also integrable. Okay. Non-integrable. Actually, you know what's the integral of it. What's the integral of F plus G from A to B? It's simply equals to the integral from A to B of F plus integral from A to B of G. Good, very good. How about the other part of linearity? Scalar multiple. Okay, scalar multiple. So if you take any scalar from R, K times F is also integrable. Not only you know that it is integrable, you know what's the integral of Kf. What's the integral of Kf? Yes, it's simply just the constant K times the previous O integral. Okay, you can pull the constant out. Okay, in a layman word. So this is linearity. What else? What else? If your function is always positive, what can you think of the integral? Is also positive. Okay. Is this easy to imagine or not? Is this easy to imagine using our definition? If your fx always lies on the top of what is that line? X equals 0. Where's your rectangle? Your rectangle is always positive, right? Okay, so that's why the integral should be greater or equal to 0. But to be precise, you need to go through the rigorous proof. Okay, you need to prove it. Okay, you need to prove it using the upper sum or lower sum. Okay, just now what I said is just like summarizing what's going on. Okay, describing what is happening. Not in detail yet. Okay, what else? We can split the domain. Correct or not? So let's say if A less than C less than B, if we want to integrate from A to B of fx dx, what we can do is we can split the domain. We can do AC first, and then we can integrate CB. Okay, we can split the domain. Okay, this is allowed. So to prove this statement, what do you need to show first? You see, I only say that f is integrable from A to B. Do we know that f is integrable from A to C and C to B or not? I didn't give you this assumption. Do we know it? We have to show it. Okay, so this is a lemma. So you need to first show that fx is integrable
on AC so that this quantity here defined. And then we have to show that F is also integrable of CB so that this quantity here defined. And then once these two defined, the next job is to show that the sum of these two numbers is simply the integral from A to B. Okay? But to show equal, right? How to show? Come back again. How to show two things is equal? The difference is equal to 0, or the difference is less than epsilon for all epsilon greater than 0. Okay, so this is what you need to do. Yeah, this is what you need to do. What else you need to know? More. So for example, integral is order preserving. Okay, what do we mean by order preserving? If fx is less than or equal to gx, then for all x in AB, then what? The integral also follow this inequality. So meaning integral of fx should be less than or equal to integral of gx. Okay. How to prove this statement? This statement should follow from part 3. Is it part 3? Not part 3. Which part? Part 2. Correct. If fx less than or equal to gx, you can see that gx minus fx is actually greater or equal to 0. Okay, and then you can show that integral of gx minus fx is greater or equal to 0. But how to get to this section? You use linearity, yes. Okay, so for this proof, right, you don't need to go through the upper summa, lower summa, epsilon, what? Because those hard work you have done in part 2 and then the linearity part. Okay, those hard work is done there. Okay, so this part 4 is really just follow from what you have proven. Okay, one last thing is, how about the integral of absolute function? Okay, if f is integrable, then absolute function is also integrable. Do you know what does this absolute function does to f? What's this absolute f? It makes the f positive. Correct? Okay, it makes the f positive. So the result is the integral of dx absolute value is less than or equal to the integral of this absolute function. Okay. Make sense? Okay. Okay. Okay, so for now, we will postpone these proof first, and then we will go through what we want to achieve, and then we will come back and talk about the proof. For the proof here, we will either prove next time, or we will left as an exercise. I think we will take some of them as a practice in class. Okay, for next class. I think this class, you know why I don't like to teach analysis? Analysis is very, how to say, mind consuming. Mind consuming is not that you need to think a lot, but you need to, how to say, process a lot of things. You just need to process it. It's not, sometimes it's not very hard to think, but you just need to go through the hard process. Like the epsilon delta, you need to do estimate like that. Okay, it's not that it's very hard to construct the partition or what. It's just when you go through the argument, like maybe the n will get very large or you want to make it very small. This kind of thing is very subtle. Very subtle. So you need to put a lot of, how to say, effort into checking whether I use the right n or not, I use the right epsilon or not, I use the right delta or not. It's not like algebra. If it's algebra,
almost everything follow from definition only. You just use definition of maybe say group normal group isomorphism. You just check definition. Okay, good. But analysis you need to compute. Okay, you need to compute. Not only you need to compute, this computation is quite abstract. You don't see number already. You only see epsilon. You only see delta. You get what I mean? Okay. So this is a challenge for analysis. Okay. Not only you need to know what's going on, you need to use the right estimate. Okay, so that it works. Okay. All right. So what other theorem you can see from this integration section? So the next theorem we will see is this integral mean value theorem. Okay, integral mean value theorem. So what does it say? If f is continuous, if f is continuous, what does it mean? It implies that this function is what? Integrable. Okay, if it's integrable. So in particular, then there exists some c in AB such that fc is equals to 1 over b minus a integrate from a to b fx dx. Okay. A bit special this mean value theorem. It says that if you integrate this function from a to b, and then you divide them by its length, there's some function that, there's some value that realizes this number. Very special, this one. Remember how you get integral? You make sure the upper sum and lower sum, right? When you increase your partition, maybe they agree, right? Okay. So the area under the curve is not really a rectangle. But you divide this number with the width of the big rectangle. And somehow there's some value of f that realizes this number here. You get what I mean? So this means what? Okay, if I rewrite this, inequality is what? B minus a times fx equals to the integral of fx dx. What does this mean? What does this mean? On the left-hand side here is what? It's a rectangle. This says that your irregular area can be realized as some area of some rectangle. And then this length is given by one of your value of your f. Does that make sense? Very special, Can you imagine this in picture or not? Can You want to try and draw it? Want to try and draw? 不要 try， 你不要这样害羞的，没有害羞的，会害羞。Yeah, in picture 长怎样？快来看。Okay, suppose you have a continuous function, good. 我变成它的那个说书人了。Okay, suppose you have a continuous function and then you want to FC 要不要用那个颜色？用这一排颜色比较亮，这个颜色比较暗，用这一排的颜色。呀，用这一排的颜色。这个不要。Okay, suppose you have a continuous function, and then there's some point, this point here maybe. Then this part equal to this part. Not quite. Okay, right. So which part is equal to which part? Which part is equal to which part? So let's zoom in. Never mind, you can stay here first. So you see, so what's this statement saying about? The area under the graph, so maybe the whole part here, is equals to the rectangle defined by this FC times B minus A. So use which color easier? Maybe use wait, let me make this clear first. So is equal to this rectangle here. Now B, where's B? Okay, too far. Let us move B in. Okay, here. Okay, so we can see that the pink box is equals to the, okay, not pink box. So the pink part, wait, let me remove this. So the pink part looks like this, right? Is equals to the yellow part like this. Okay, yeah. Does it make sense? Okay, yeah. Oh, it's equivalent to what you say. Oh, it's equivalent to what he said, right? Is it equivalent to what he said? Because they coincide here. Correct, correct. No? So the difference here is the non-intersecting part is this pink part and the yellow part. Yes, it's equivalent to what you said. Okay, so this part here is equals to the pink part. Okay. Good, very good. So do you first think of so Jack, do you first think of this one first or you think of this one? This one first, This one first, Okay, okay, good. Oh, it makes sense. If you suddenly think of this one, then you are a bit genius. Okay or not? Yeah. Yeah, good, 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 very good. And this proof actually is not hard. And then it uses absolute value theorem, intermediate value theorem. And this proof. Not hard, but very, very good use of what we have proved. Very short proof, actually, this one. Okay. We will see, we will prove, either we will prove it next time or not. And then I want to introduce this fundamental theorem of calculus. Okay, very important. Later, I will show you example why this fundamental theorem of calculus is kind of important. Okay, FTC. Actually, this is what we call the FTC. Right? So what is FTC? There are two statements of it. So if a function is integrable, okay, and you have a big F, remember how we call this big F? We call it the antiderivative, right? Okay. If this big F satisfies the derivative equals to little f for all x in the domain, then what? Then the integral from a to b fx dx is equals to fb minus fa. Hey, this theorem is very important. If don't have this theorem, you cannot do your integral, you know? Do you know that? How do you do this integral, for example? Let's say 0 to 1 of x squared dx. How do you do this integral in calculus? You take x cubed over 3 evaluate from 0 to 1, right? What's this step? This step is a magic step, you know. Don't you think this step is a magic step? Because you go from something with integral sign to something don't have integral sign. Actually, this step is a magic step, you know. So this magic step require proof. Require proof here. So why is it true that if I do this integration, I just substitute this into it, and then I take away the other substitution? Why is it true? This is fundamental theorem of calculus. Okay, where the big F here is what? Who is the big F here? The little f here is x squared. What's the big F here? Capital F here is s cubed over 3. Correct or not? Correct or not? And then f prime x is equals to little fx for all x. You get what I mean? So the high school, when you do this max, this is really a miracle. Okay, how to go from this integral to this nothing without integral. Is this miracle here?
FTC. So how to use the FTC? You need to make sure that f prime x equals to fx. Okay. If this is true, this big F, what you call it? It is the antiderivative of small f. Okay, because because x derivative is f. So if you want to go from small f to big F, you need to go back before the derivative. So we call it an antiderivative. Antiderivative.
Another statement of FTC is this. So let G be an integrable function. Okay, and we define capital G A B to R by this function here. This is a very important result because this is how we define a logarithm function here. Okay. We have an integrable function. Okay, since it is integrable, right? So we integrate it. Okay. How do we integrate it? We integrate it from A to some x, where x is in between A and B. Can or not? Can we do this? It is integrable for the whole domain A to B. So meaning I can pick any two number inside there and then I integrate my G. And then this will give me a number. Okay. And then now I study how this number changes. Okay, how this number changes. Starting from A to some point at in between A and B. How this number changed when S changed. Okay, this become a functional, correct or not? This part here is really about a number. So this function is going from AB to real number because this integral here should be a finite number. Make sense? Make sense or not? So this thing here, this should be a number. Okay, this integral here. Because it's integrable, integrable means what? Upper integral equals to lower integral. It's a number. Okay, it's a number. Okay. So in particular, this function is continuous. Okay, we can show that it is continuous. And moreover, because G is integrable doesn't imply that G is continuous. But if G is continuous, then we can show that this capital G is actually differentiable. Not only differentiable, you get what you want. What do we want? We get that G prime X is coming back to Gx, which means you differentiate. This is a Lohau project. You differentiate the integral from A to X, Gt dt equals to Gx. Okay. Okay, you differentiate an integral, they cancel out. But this is only true when G is continuous. If not, might not be true. Okay. Okay, so I will include all this proof inside today's lecture note, and then if I will think to see whether we want to revise any of them in the next lecture, and then we will do it together, prove some of it. Okay. Otherwise, you can read first. When I posted out the lecture note, you can read the proof first, or you can try and practice first, and then we can do it together in the class next time. Okay. All right. Any question before we break? No. Okay. If not, okay. See you next week.